You can start.
Yeah. So good afternoon. Are all the students here? At least many of them. I see some of them. I would like to know how many of you have seen. The first thing to begin with. On Monday, we start the class at 3. This is very important because I have something at 4. I would like to finish by 4. So it's impossible that we start at 3:30 and hence we start at 3. I suppose that's all right with everyone. So Monday we start at 3. The next class is on Monday. Okay. Please remember this. I shall also give a reminder on Monday morning. And how many of you have seen a completeness argument? For example, the fact that Cx is complete for X compact. You need to tell me somehow. I mean, unmute yourself and tell whether you have seen this or not seen this. You know about this, don't know about this, what?
So, we have seen this. We have to take any two Cauchy sequence and prove that the converging point also belongs to Cx.
So you first have to prove that it converges. So there are 2 parts. Okay, so someone has said that she has seen it. What about others? You need to speak up. Okay, I'm asking something.
Yes, sir, I have seen.
Yes, sir, yes, sir.
Anyone who is not comfortable with this fact? I need to know this. Anyone who is not comfortable with this fact? There's nothing wrong in acknowledging that. It's not your fault if you don't know this. If there is no response, I shall assume that everyone is comfortable.
We are comfortable. So we are comfortable.
Okay. Someone, is Pooja Sharkar here? Pooja Sharkar doesn't seem to be here. She, okay, fine. All right. So you saw that Cx for compact X is a complete normed space. So it's a normed vector space. First of all, it's clearly a vector space. If you add continuous functions, you get continuous functions. If you multiply a continuous function by a scalar, you get a continuous function. So it's a vector space. You can give it a natural norm. And it so happens that under that norm, it's a complete set. That is, Cauchy sequences converge. This has some advantages. So that's the first example of a complete normed vector space. That's the first example you should see of a complete normed vector space. A complete normed vector space is called a Banach space. After Stefan Banach, who was a Polish mathematician. Okay. How do you decide whether a normed vector space is complete or not? You check by hand for examples. For example, for Cx, you can check that it is actually complete. For a certain class of, a certain class, for a certain class of normed vector spaces, we are going to prove it today or in the next class that they're complete. So for various specific cases, you can prove by hand. Well, I hope to show you at least one thing, one example, other than CX, which is today, which is complete. It's best to start with, maybe it's best or not, I don't know, but I would like to start with a general criterion. It's a very nice general criterion. So here is a theorem. This is not there in this chapter of Rudin. It's not there in the third chapter of Rudin, but I am including it because this is a very good way of starting it. Normed linear space is a vector space. By the way, when I talk of a normed vector space and convergence, there is it clear to everyone that I'm talking about the convergence in the norm of the space. So if we are in Cx, and if I say Fn is a sequence in Cx, then Fn converges to X if norm Fn minus X, the Cx norm, that is the uniform norm. So Fn goes Fn minus F, the uniform norm, that is sup over X in X mod Fnx minus Fx, that goes to 0. We say that it's Cauchy if the sequence Fn is Cauchy in the norm of the space. So suppose you have a normed linear space X, and then if I have a sequence of vectors there, if I talk of the convergence of the series summation Fn, what do I mean? I mean, if I look at the partial sums, they converge in the norm of the space. Is that clear?
Yes, sir.
Right. So that is the last line. When I talk of the convergence of summation Fn, that's what it means, that it converges in the norm of the space. Everything is the same as complex series. There's nothing different. I mean, whenever you had modulus, you will put the norm, everything goes through. If you think of it, when you learn sequences and series of complex numbers, for convergence, Cauchy, etc., all you used is the property of the modulus. Now, properties of the modulus of complex numbers and of norms are same. Norm is modeled on the, a definition of a norm is modeled on properties of the modulus of complex numbers. So whenever you can use modulus of complex numbers, you can use a norm. Okay, so convergence of summation Fn or convergence of a sequence Xn in X is exactly in the norm. If I say the sequence Xn is Cauchy, it will mean that in the norm of the space X, that is norm of Xn minus Xm goes to 0. Fine. Okay, so note that this is a rather peculiar kind of statement. It says that, so it's an if and only statement, right? So I'll separate the if and only part. So first it says that if X is a Banach space, so that means if it's a complete normed space, then for every sequence Fn, if summation norm Fn is finite, then summation Fn is finite. So in a Banach space, if you're given a series and you are told to check the convergence of the series, all you have to check is consider the scalar series summation norm Fn and just check whether it's convergent or not. You are done. Conversely, if you're given a non-linear space, and if it has the property that for every sequence, if it has the property that for every sequence Fn of vectors, summation norm Fn less than infinity implies that summation Fn converges in X, then X is complete. That's the content of the statement. I hope it's clear. If not, tell me now. Let X be Bana. Remember, that means that it's complete under the norm. Then let okay. If M greater than N, let's say, then it is by definition of the partial sum. So M is greater than N, N is less than M. Okay, anyway, it's less than equal to, and that is so since X is complete, Cauchy sequences are convergent. And you are done. Because the sum of any series is just the limit of partial sums. Clear?
Yes, sir.
So this is, yeah, this is very simple, okay? Conversely, so conversely means what? Conversely, suppose X is a non-linear space with the property that whenever a sequence Fn has the property that summation, whenever a sequence Fn satisfies summation norm Fn less than summation norm Fn is convergent, then summation Fn is also convergent. We have to show that the space is complete. So let Gn be a Cauchy sequence. We have to show that Gn converges. Okay. So somehow we have to use the series criterion, right? That's the only information we have. That when that X has the property that for any series, if summation norm Fn is convergent, then summation Fn is convergent. This is all we can use. So this means we have to produce a convergent series of scalars to begin with. Choose N1 such that norm Gi minus Gj is less than 1 for Ij greater than equal to N1. This is possible because Gn is Cauchy. Okay. That's the definition of Cauchy sequence. Apply induction. Having chosen N1, N2 up to, let's say, N capital N, choose N capital N plus 1 greater than N capital N such that norm Gi minus Gj is less than 2 to the power minus capital N for ij greater than equal to n plus 1. Okay. Let fk equal to gnk minus gnk minus 1. For k greater than 1, and f1 is just gn1. So do you see what I did? Look at this paragraph. This is a very standard construction, by now standard. Okay. So note that if I sum f1 plus f2, I shall get gn2 minus gn1 plus gn1. So I get gn2. And now it should be clear that if I sum from f1 to, let's say, fk, I shall be left with only gnk. Okay. What we know is summation norm fk, k equal to 1 to infinity, is equal to summation k equal to 1 to infinity, maybe, well, 2 to infinity, norm gnk minus 1, and that's actually finite. You know, that is why these things have, that is how these things have been chosen. Is that clear? This is the geometric series, powers of 2. So I don't even have to compute what it is, but it is finite. So summation k equal to 1 to infinity norm fk is finite. If you put k equal to 1, you will get norm gn1, which is something finite. The rest of the series is powers of 2. I mean, negative powers of 2, geometric series. So I produce such a thing. So by the property that X has, summation fk is finite. But what the hell is this? As I told you, the partial sum up to the stage n, or let's say partial sum up to the stage L, let's say, will only give you GNL. So given a Cauchy sequence, we have found a subsequence which converges. And if a subsequence of a Cauchy sequence converges, then the whole sequence has to converge. The proof is exactly the same as complex numbers. As I told you before, have been telling you before, we replace the modulus by the norm. The idea is that Cauchy sequence is something where the terms keep on getting closer and closer. They can't go far from each other. And then if there is a convergent subsequence, all other terms go to the same limit along with this convergent subsequence. Okay, so we have found a criterion for showing that some space is complete. In some cases, we might be able to use this criterion. Okay. Fine. Oh, no. Before I progress any further, I need a lemma, a theorem, for which we went into convex functions yesterday. I need that theorem. Without that, I won't be able to progress. My aim is to study certain complete norm linear spaces, but to show that they are actually, maybe I don't need that to say something. Just give me a second. Or maybe not. Okay. Let me try. I shall need it eventually, but we'll do it when needed. Suppose this is a measure space. Let L1 mu denote all measurable functions. I'm not writing everything, but when I write F and I'm in the context of a measure space, I'll always mean measurable functions. F such that complex value can be complex value. Complex valued measurable function, complex numbers with the usual Borel sigma field. It's R2 as far as measure theory is concerned. Just okay, maybe I write this as a slightly curly L or something because I'll have to do something to this. So this curly L, calligraphic L1 mu stands for the set, just the set of all functions for which integral mod f d mu is finite over the whole set X, of course. Okay. Now, unfortunately, what might happen is, sorry, not P. You could have non-zero functions for which integral mod f d mu is 0. I mean, this of course depends on the measure, but even for very nice measures like Borel measure on the Lebesgue sigma on the Borel measure on the Borel sigma field, you have Lebesgue measure on the Borel sigma field. You have functions whose, I mean, the function is non-zero only on a set of measures 0. And strictly speaking, they're not zero functions, but the integral is 0. This is a problem. Okay. So I'm almost, as you can see, I'm almost at the stage of giving this set L1 mu a norm, but this set N1 mu is spoiling the game so far. Okay, first thing to note is that let Fg belong to L1 mu, then integral mod f plus g d mu is less than equal to integral mod f d mu plus integral mod g d mu, simply because mod f plus g is less than equal to mod f plus mod g. That's why. So finite, because both f and g have been assumed to be in L1 mu. And of course, if you multiply by a scalar, and if integral mod f d mu is finite, replace f by a scalar times f, the finiteness remains the same. So L1 mu is a vector space. Okay. And turns out that this N1 thing is a vector subspace. For the same reason, if f and g satisfy integral mod f d mu is 0, integral mod g d mu is 0, integral mod f plus g d mu is less than equal to integral mod f d mu plus integral mod g d mu equal to 0, less than equal to 0. It can't be anything less than 0 because mod f plus g is a non-negative function. So integral mod f plus g d mu is also 0, and same for scalar multiplication, of course. So N1 mu is a vector subspace. So you can quotient a vector space by a vector subspace. So now this straight L1 mu equal to this curly L1 mu divided by N1. I hope this is clear that I'm quotienting a vector space by a vector subspace. This is very standard, and I hope all of you are conversant with that. If not, either let me know now. You can, I mean, just speak up that you are not comfortable with this.
Okay, sir.
Okay. So now note that, okay, the elements of this quotient straight L1 mu are really cosets. So they're things like F plus N1 mu, but we don't write that. We always write F belongs to L1 mu, that is as a function, okay? But you must remember this is the coset. That shows right now when I'm defining the norm. What I really mean is I take a coset. So any coset is of the form F plus N1 mu. Now, of course, it's quite possible that F plus N1 mu could also be G plus N1 mu, but then F minus G will have to be in N1 mu. F plus N1 mu, this is standard quotienting. F plus N1 mu can only be equal, F plus N1 can only be equal to G plus N1 if F minus G is in N1. If F minus G is in N1, then integral mod F d mu is the same as integral mod G d mu. That is why I can choose any representative and declare this norm of the coset to be actually just norm of any of the representatives, integral F d mu. Now note that if the norm is 0, that is norm of the coset is 0. By the way, it has all other properties of norm. Triangle inequality, etc. is pretty clear. So this technicality about N1 is to ensure that if the norm is 0, then the element is 0. So when you do the if norm of F1 is 0, then this means norm of the coset, that is F plus N1 mu, that thing is 0. How could it be? If only if F belongs to N1 mu. In that case, F plus N1 mu, the coset is equal to N1 mu, and N1 mu as a coset is the 0 element of the quotient. That's why. Now it's a genuine norm. Clear? So I have, so L1 mu with this norm is a norm linear space. So let me show you that L1 mu is complete. So what do you have to show? That proof. Be a sequence in L1 mu such that, how shall I show that it's complete? I could show that every Cauchy sequence is convergent. Alternatively, I could use the theorem that we just proved, that a linear space, to show that it's complete, norm linear space, to show that it's complete, all I'll have to show is that if Fn is a sequence such that summation norm Fn is a convergent series of positive numbers, non-negative numbers, then summation Fn is a convergent series in the space. I'll only have to show that summation Fn is a convergent series in the space. That means summation Fn is an L1 function. But now you have just learned measure theory, right? Now probably you are already able to see that there is nothing to prove now. There is something called dominated convergence theorem. I'll write out everything so that you can immediately apply dominated convergence theorem. Such that this is what is given. Take your favorite version of dominated convergence theorem. For example, the version stated in Rudin, the book Real and Complex Analysis, tells exactly what I'm going to write. This is exactly the statement of dominated convergence theorem. One of the statements. I mean, any famous theorem can be stated in 2-3 different versions. But I think this is exactly the statement that appears in Rudin's Real and Complex Analysis. Then dominated convergence theorem assures you that summation fnx converges for almost all x with respect to the mu measure. Moreover, if the sum is called f belongs to L1 mu, that is integral mod f d mu is already finite. And moreover, integral f d mu, not mod f, but integral f d mu you don't need anything more. All you needed to show is that the series summation fn converges in the L1 norm. Now it tells you that fn actually converges for almost all x. If something converges for almost all x, it converges in L1 norm because of the obvious reason. And so that completes the proof. Okay. Any doubt? Okay. So this shows by an application of what I did right in the beginning that that L1 mu is actually a complete norm space. Now we become a little more ambitious, and instead of L1, that is instead of integrating the modulus, we want to integrate a little something else. Now for that, I need the theorem that I was mentioning before. So when p is equal to 1, I'll take q equal to infinity and vice versa. A positive measure space, okay. just to be absolutely sure. So f and g are non-negative functions. Oh. Sorry, no modulus required because f and g are non-negative functions. We shall apply to modulus of certain things. At the moment, they're just This is because instead of L1 that we considered earlier, we want to consider a class of functions with a different norm. And for that, to show that that class of functions is a vector space, I need this. To even show that that's a vector space. For L1, showing that it's a vector space was not a problem because we just used triangle inequality of modulus. It's not the case here. I'll need this. Okay. P. If A is equal to 0, then integral f to the power p d mu is 0, which means, well, everything is non-negative. So f to the power p is 0 almost everywhere, then there is nothing to prove. That means f equal to 0 almost everywhere. So hence fg equal to 0 almost everywhere. So done as far as the first equality is concerned. I mean, for both, right? Okay. If A greater than 0, and so the only case to consider is A positive. But if A greater than 0 and B equal to infinity, I mean, same for B equal to 0, of course. If B equal to 0, then also there is nothing to prove. Okay. If one of them is positive, a positive number, and the other is infinity, then also there is nothing to prove. Why? Because the right-hand side of both inequalities are actually infinity. So then the left-hand side, whatever it is, will be less than equal to that. So assume 0 less than A less than infinity and 0 less than B less than infinity. If one of them is infinity, then there is nothing to prove. If one of them is 0, then also there is nothing to prove. So both So the only case that we need to consider is both are between 0 and infinity. Then integral f to the power p d mu equal to integral g to the power p d mu equal to 1. Because they have precisely been divided by the appropriate things. Okay. Take a point x such that fx is something between 0 and infinity and gx is something between 0 and infinity. You are guaranteed such a point. Simply because a and b both are between 0 and infinity. For such a point, well, because fx is a positive number, it can be written as e to the power something. Since gx is a positive number, it can be written as e to the power something. It's just that that something I've taken in such a way that in one case it looks like s by p, in another case it looks like t by q. I can always do that, right? But remember, what is q? Well, 1 by p plus 1 by q is 1. By convexity of the exponential function, we have this is a convex combination of the points s and t. So by convexity of the function, this is 1 by p e to the power s plus 1 by q e to the power t. This is exactly what we discussed yesterday. We have 2 points s and t. I'm taking a convex combination of them. The value of the function at the convex combination is less than equal to the same convex combination of the values of the functions at those 2 points. Translated in terms of f and g, it says this is just fx times gx less than equal to 1 by p fx to the power p, because fx is e to the power s by p. Agreed? Okay. Now, this holds for any x at which capital Fx is between 0 and infinity and capital Gx is between 0 and infinity. All right. Now, note that these points are almost everywhere as far as mu measure is concerned, because if Fx was 0 on a set of positive, no, I'm sorry. If Fx was infinity on a set of positive measure, then the integral, then capital A would be infinity. We are not allowing that for a good reason. Fx, of course, can be 0 on a set of positive measure, but we can disregard that, right? I mean, integrating that will only give us 0. So there is no need to look at that part of the set where Fx is 0, even if it has positive measure. It's just that that part cannot be the whole set. Okay. So integrating so when I do this integration over the whole set fg d mu, I don't care about the part on which it's 0. It doesn't matter. It contributes as 0. And there is nothing of positive measure on which it is infinity. Okay. So I only care about those points which satisfy the first line on display now. And for those points which satisfy the first line on display, I have this. So consequently, I'll have, this is 1 by p integration capital F, which is 1, f to the power p, sorry. And integration capital F to the power p is 1 because of the last line on the display now. Okay, same for integration g to the power what do we have for g to the power q? I need for g to the power q, but I have g to the power p. Why is it so? Just a minute. Give me a second. Oh. I'm sorry, I need Q here. I'm changing B. Please take note. I'm changing B because I'm really proving the first inequality now. So I'm changing B. Please take note of that. And consequently, this will change. That's all, okay? I've changed B, which is at the end of the top line. And because of that, the last line changes. It was g to the power p. It's now g to the power q. Now everything is correct. Is that okay?
Yes, sir.
And that's exactly what I need for the first equality. Okay, this thing is integral over x f by a times g by b d mu, and so that's equal to integral f g fg d mu divided by ab, and that's less than equal to 1. So and that's what you wanted to show. Again, let's go back to the definition of AB. A is this and B is this, as in the top line of the screen now. And look at what we wanted to show in the first inequality. I was trying to show just this. That is, I wanted to show that integral small f small g d mu is less than equal to AB. That's what I have shown now. So how did we show that? Well, we defined this capital A and capital B, ruled out the possibility that one of them is 0 or infinity. So both have to be between 0 and infinity. And then consequently, it's enough to look at only those points in the whole set for which the functional values are strictly between 0 and infinity. Convince yourself that it's enough. And then I can integrate, and the straightforward use of the exponential function gives that. Convexity of the exponential function gives it. For the second inequality, okay, let's go back to see what the second inequality was. The second inequality, where is it? Oops, sorry. Yes, this was the second inequality. Here both have power p. There is no q here in the second inequality. By the way, this is called Holder's inequality. The second one is called Minkowskis. Okay, for the second inequality, write f plus g to the power p is f into f plus g to the power p minus 1 plus g into f plus g to the power p minus 1. Now, note that integral f into f plus g to the power p minus 1 d mu is less than equal to integral f to the power p d mu to the power 1 by p times integral f plus g to the power p minus 1 I already have. I shall have to multiply this with q d mu whole to the power 1 by q by Holder's inequality, which we just proved above, applying just that.
So there p minus 1 is missing in left hand side.
P minus 1 is missing somewhere.
F, yeah.
Okay. Same thing for G. Again by Holder's. So I apply Holder's inequality twice. So first I do this step with the red tick. And then the two terms on the right hand side I handle by Holder's. I have to add them, of course. Adding, we get, what do we get? Integral f plus g whole to the power p d mu is less than equal to integral f plus g whole to the power p minus 1 times q d mu. This appears in both the terms. So I'll take that out. But what is p minus 1 times q? Remember, 1 by p plus 1 by q is 1, which is the same as p plus q is pq. P plus q is pq. That's the same as saying 1 by p plus 1 by q is 1. And if p plus q is pq, then p minus 1 times q, which is pq minus q, is just p. But I have a to the power 1 by q. Now we're in good shape. So I bring the first term to the right, left-hand side and divide by it. So then I'll get integral f plus g to the power p d mu whole to the power 1 minus 1 by q. 1 minus 1 by q is 1 by p. That was the second one, Minkowskis inequality. Minkowskis inequality. Now, for whatever time we are left with, note that armed with this, define, say, such curly LP mu equal to, well, f such that integral f to the power p d mu is finite. Let NP, okay, 1 less than equal to p less than infinity. The p equal to infinity case will have to be treated differently, which we'll do tomorrow on Monday at 3 o'clock. This is only for p strictly less than infinity, greater than equal to 1. And think about what goes wrong below 1. Why can we not do it below 1? Okay, this is equal to, well, I don't really need that. Now, Minkowskis inequality, which is now the top line in the screen, will immediately tell me that the script LP mu is a vector space. If f and g are there, then f plus g is also there. I needed that. That was the purpose of proving Minkowskis inequality. And once I know that this LP mu is a vector space, it's okay. NP mu, NP is a subspace of LP for the same reason, because of Minkowskis inequality. So quotient LP by NP and do exactly what we did for L1. So let LP okay. And again, this is a vector space of cosets really, but as before, these are equivalence classes of functions, but in common parlance we call functions, but we must remember, but these are really equivalence classes of functions. This turns out to be a genuine norm in this case. Triangle inequality is proved by Minkowskis. Quotienting by NP ensures that there is no element whose norm is 0, but the element is non-zero. So LP mu is a norm linear space. Okay. So time is over. Let us stop today. In the next class, we shall start with this and show that this is a complete norm linear space, which requires a little more effort. But that's why I asked whether you know the proof of CX being complete. You see, the strategy is the same. What is done in CX is you start with a Cauchy sequence that is uniformly Cauchy. That implies it's pointwise Cauchy. The moment it is pointwise Cauchy, it has pointwise limits because complex numbers are complete. In complex numbers, if you have a Cauchy sequence, it's convergent. Once you get hold of the pointwise limit, there are two things to show. That it is also actually uniform limit. Second, it belongs to the set of continuous functions. So you first show that it's also uniform limit. Second, you show that uniform limit of continuous functions is continuous. So here also the same thing is done. You start with a Cauchy sequence in LP, get down to pointwise, show that almost everywhere, in this case almost everywhere, it's convergent. So get the almost everywhere limit and show that that's actually an LP limit. Okay. Any questions?